Okay, wanted to review a little bit about rotational inertia, and then we'll move on to rotational momentum. Okay, so if I were to roll these different shapes, so this is a hollow pipe, okay, like a piece of pipe. This is a solid sphere, like a golf ball, okay, and this is a solid cylinder, like a C battery or a D battery or something along those lines. Which is going to win? Okay. Now, in order to win, they need to rotate. Okay. Which is going to be the easiest to rotate? Okay. The one that rotates the easiest is going to be the one that wins the race. Okay. Now to help you out, I've got the equations listed here. Which has the least rotational inertia, and that'll be the easiest to rotate. Well, this has got 1 mr squared. This has 0.4 mr squared, and this has 0.5 mr squared. Okay, so 0.4 mr squared is going to be the least. Okay, and then mr squared, 1 mr squared is going to be the greatest, and half mr squared is in the middle. So this one has the least rotational inertia, which means it's going to roll down the slope the fastest. This one has the greatest rotational inertia, which means it's going to roll down the hill the slowest, and this guy is going to be in the middle. So if we were to roll all three of these down a hill, what order they would come in is solid. We'd have golf ball beat C battery, which would beat pipe, and pipe would come in last. Okay. All right. Let's see. So Newton's first law of linear motion was F equals ma. I'm sorry, Newton's second law of linear motion was F equals ma. Okay, if we apply this to rotational motion, we're going to change these into some Greek characters. Okay, instead of talking about force, when we talk about rotational motion, we talk about what? Torque. Okay, and so the symbol is a tau. Okay, instead of talking about m for inertia, okay, the symbol for rotational inertia is I. Okay, and the symbol for rotational acceleration is this fish shape. Okay, tau equals I alpha. So this is Newton's second law written for rotation. Torque equals inertia times acceleration, which is very analogous to force equals mass times acceleration. Okay, and again, I always give you the equations if you're going to need them. But you need to be able to interpret them. So for a given object, for a given rotational inertia, what's going to happen to alpha if I increase tau? Okay, if I apply more torque, what's going to happen to the rotational acceleration? It's going to increase. Okay, this equation tells you this. If I make this bigger, okay, then this side's going to get bigger too. If I stays the same, then alpha's got to get bigger. Okay, so the more torque you apply, the faster that something spins up. Okay, now for a given amount of torque, okay, if I goes up, what happens to alpha? Okay, if rotational inertia increases, what happens to rotational acceleration? Okay, so you can think about this mathematically. If this side of the equation stays the same, okay, and this side goes up, what has to happen for this guy in order for this to remain the same? No, it's got to go down. Okay, or you can think about it in terms of physics concepts. What happens to the rotational acceleration if you increase its inertia? Okay, it's going to resist changing its rotational state, so its inertia or its acceleration is going to go down. Okay, so for a given torque, the bigger the rotational inertia, the slower its spin rate will change. Okay, so here we've got two block and tackle systems that have 500 gram wheel and axle systems. It shouldn't be block and tackle systems, but they have 500 gram masses attached. Compare the rotational accelerations. Okay, everything is the same except the fact that this one is placed at a greater distance from the axis of rotation. So these are pulleys, and they're going to spin around like so, or more like that. Okay, now what effect is increasing the distance, increasing the distance that this is attached from the center? How is that going to affect it? Well, it's going to increase the torque. Okay, what is increasing the torque going to do to its acceleration? Okay, what is increasing force do to acceleration? It increases it. Okay, so because this has more torque, this is going to have more acceleration. Okay, let's say I push both of these with the same force around the edge, so I'm creating the same torque. Which of these is going to accelerate faster? Okay, so I'm pushing these around the edge. Which of these is going to accelerate faster? Well, this guy here has less inertia. Okay. This guy here has greater rotational inertia. So which is going to be easier to spin? The one with less inertia and the one with more inertia? It's going to be the one with less inertia. Okay. Alright. Any questions? Good. So that's my bit on that. So what we want to do is move on to rotational momentum. Kind of going through a lot of it's kind of odds and ends today. So remember momentum. P equals what? Okay, P equals inertia times speed. So mass times velocity. P equals m times v. All right, so that's what we've dealt with before. Now we're going to do with rotational momentum. Okay, now the symbol for rotational momentum is an L. Okay. Why they picked that, I really don't know. Probably should Google that, but I really don't know. Okay. Instead of talking about mass for inertia, the rotational inertia symbol is called the I. Okay. And here we've got velocity. The symbol for rotational velocity. Oh, I wonder if anyone remembers the symbol for rotational velocity. It's the W kind of thing, right? So that is the symbol. It's a lowercase omega. It is. This is the symbol for rotational momentum. We're not going to be doing any like real math with this per se. Not that we couldn't do kind of real basic like. But you probably want to jot down the equation just to have it anyway. Okay. So if the disks are equal, which disk has the greater rotational momentum? Okay. Well, the disks are identical. Okay, the disks are identical. This disk is obviously rotating at a greater rate. Okay. So the one that's spinning faster is going to have more momentum if it's got the same rotational inertia. Okay, so the greater rotational velocity, the more momentum you have if the mass is the same. Okay, so here we've got two disks. What's the same between them now is that they're rotating at the same speed. Okay, and the question is which of these disks is going to have a greater momentum? Okay, well this disk is thick and this disk is thin, so we can make the assumption that this has more mass and more rotational inertia. So since it's got more rotational inertia, greater I, it's going to have more momentum. So the bigger the rotational inertia and the bigger the rotational velocity, the more rotational momentum you have. Okay. Let's say we've got a solid disk and a hollow disk. Now let's say they have the same mass. Okay. Which has the greater momentum in this case? Well, they've got the same velocity. Okay, so that means that the one that's got the greater rotational inertia is going to have the greater rotational momentum. So which one has the greater rotational inertia, or would it be the same? Well, what's different between these is the shapes. Okay, What determines the rotational inertia? Not just the mass, but the location of the mass. The further away you get the mass from the axis of rotation, the greater the rotational inertia. Okay, so this guy has mass all the way from the radius to the axis of rotation. This guy right here has pushed that mass away from the axis of rotation out some distance. Okay, because the mass is concentrated further away in this system, it's going to have a greater rotational inertia. And because it's got a greater inertia, it's going to have a greater momentum. Okay. Now, linear momentum is conserved if there's no outside forces. Okay. Rotational momentum is conserved as long as there's no outside or external torques. Okay. So another way we can say that is that my initial, if something is conserved, your initial equals your final. Okay. L, remember, L is the symbol for rotational momentum. Okay, so L1 equals L2. Okay, L equals I omega. I know we're kind of going through a lot of different things here today. So I1 omega 1 equals I2 omega 2. Okay, might jot that down. Okay, so what this means is your initial rotational momentum equals your final rotational momentum, assuming there's no outside torques. But that doesn't mean that the speed and the inertia can't change. Okay, so if we've got a figure skater, an ice skater, and nothing is exerting an outside torque on her, then her rotational momentum is constant. Okay, this says rotational inertia. That is incorrect. Her rotational momentum is constant. Okay, why does she spin faster if she brings her arms in? Okay, so here we've got a figure skater. So this is me, and this is my figure skating leotard, and these are my figure skates. Okay, so remember, the rotational inertia depends on how you're rotating. I can change my rotational inertia by moving my body around. Okay, all right. So in this case, okay, so this is my axis of rotation. This is like spinning the tennis racket with your hands on the handle, like you're trying to warm your hands. Okay, remember this had pretty low inertia because the mass is pretty close to the axis of rotation. Okay, this had pretty low inertia. Okay, now what happens over here? Okay, if I bring my arms in all the way I can, and my legs in, okay, what's going to happen to my rotational inertia here? Okay, well, it's going to decrease. It's going to decrease even more because I'm bringing the mass closer to the axis of rotation. Okay, and what happens if I bend over like this and I stick a leg out? Okay, what I'm doing is I'm taking mass that was close to the axis of rotation and I'm moving it further away. Okay, so what happens to a figure skater if they're spinning like this and they bring their arms in? What happens to the rate of spinning? It goes up. Okay, and that's because, okay, if you bring your rotational inertia down, okay, your rotational speed goes up. Okay, if you bring your rotational inertia up, you bring your rotational speed down. Okay, this is a better way of saying that. So here we were spinning slow, but had a large rotational inertia. So big I, small omega. Okay, when I bring my arms in and do that sort of thing, my rotational inertia shrinks. Okay, and my rotational speed goes up, way up. Okay, so if you decrease your inertia, you increase your speed when you're spinning like this. Okay, and that's because there's an equal sign here. So if this goes down, in order for this to still remain equal to the same side, this has got to go up mathematically. Okay, So a tucked diver spins at 2 rotations per second. If she extends herself, quadrupling her rotational inertia, what is her rotational speed? So she increases her rotational inertia. What happens to her rotational speed? So what's going to happen to her rotational speed? Is it going to go up or is it going to go down if her inertia increases? Okay, so if inertia goes up, okay, then speed's going to go down. All right. So if her rotational inertia increases by a factor of 4, then her rotational if her rotational inertia increases by a factor of 4, then her rotational speed is going to decrease by a factor of 4. So 2 divided by 4, decreasing it by a factor of 4, is going to be 0.5 rotations per second. Okay. Normally this would be when I were to get into a wheelie chair with the little rotating spindle in it, and I would get myself spinning pretty good with a couple of masses in my hand, fully extended arms. I would get myself spinning, and then I'd bring my arms in, okay, bringing them closer to the axis of rotation going down through my body from the ceiling. And as I got those masses closer to my body, I'm decreasing my inertia, which is going to cause my speed to increase. So as I did that, my rotational rate would increase significantly, and I would get dizzy. Okay. So you can use this kind of phenomena to, or divers use this to control their angle of entry into the pool. When you're fully extended, you've got the greatest rotational inertia and the slowest speed. When you're tucked like this, you're decreasing your inertia and you're increasing your speed. And then when you want to slow your rate of rotation down again, you fully extend again, and then that slows you down. So what happens to the speed of a merry-go-round if you start in the middle and then go to the outside? Okay, so you got a merry-go-round and it's spinning like this, going around and around, and then let's say the people get out, will move to the outside of the merry-go-round. What's going to happen to the rotational speed? Okay, well, what's going to happen to the rotational inertia? Okay, well, the people move away from the axis of rotation. The rotational inertia is going to go up. Okay, and if inertia goes up, then speed goes down. Okay. All right. Let's see. I think that is it for today. Now, one thing that conservation of rotational momentum means, there's more than one more implication, but so one would mean that if we had 0 rotational inertia, and that let's say these rotors tried to spin clockwise, they were spinning around clockwise. Okay, now if I had 0 rotational momentum, and all of a sudden I have positive, or clockwise rotation momentum, okay, that would mean that my rotation momentum changed. Okay, what would happen is as the rotors started spinning clockwise, the body would start spinning counterclockwise, and that's what happens. That's why they have this tail rotor on the helicopter, to prevent the body from rotating around due to conservation of momentum. So anyway, that's it. Have a good day.